I just picked that number. If you left it uncentered, that would be the only way that you could get a school, or excuse me, a department that has a proportion of 0 is if all the students had no advanced training. And that seems fairly unlikely.
So if we center the variable, the variable is still factor.
If you say that again?
The variable is like categorical variable or
Mm-hmm.
numerical variable.
The level 2 mean is not categorical. It varies from 0 to 1. So it's a continuous variable.
So what's the purpose?
Of including that predictor or centering it?
Centering. Why?
Because a value of 0 would not be a representative value, even though it's possible. I don't know that there's any zeros in the data set. So I just moved it so that I try to keep the intercept and main effects of any interaction terms like in the middle of the data. So 0.2 is an arbitrary choice. Yeah. Did you have a question, Kayla?
I have a question about all the ICCs because I thought we were supposed to use Linux, which this has been checked themselves and probably did. But when I tried to do Linux with the code for ICC, the V4, you can't. It tells me I can't do that. So,
Correct.
But when I look at the notes, you used the prop-mixed to find it. Am I supposed to be using prop-mixed then? Or?
So for papers, so here, this is what we were just discussing actually. So when I coded the homework, I ran it in proc mixed with REML. And they pointed out that that is inconsistent with the instructions. If you run it in Glimmix and change it to be a normal distribution with an identity link, then unless you change the estimation method, it's going to be regular flavor maximum likelihood, not REML. So that's why the answers won't match. There is no V or VCore in Glimmix, so you just have to calculate the interclass correlation yourself.
And you do that by so where the UN and then 1, 1. I thought you take those, but you don't get that output so how do can you tell me how you do that because maybe I'm just not in the right spot in the notes, but how do you hand calculate ICC for Linux?
It's random intercept divided by random intercept plus residual, the same as usual.
No, I think it's a 3.94. A constant.
Not for papers, not for normal. You should have a residual variance.
For the jobs.
For what?
For jobs, because there is a binary. Binary is different from the continuous variable.
Yeah, she's asking about papers. Mm-hmm.
I was kind of asking about all of them because I tried using the output that I got with just using Linux,
Mm-hmm.
and none of the values were. I got to the point I was like, I'll just try everything and see if I'm just misunderstanding something, but nothing was working. So maybe I'll just ask you after class because it's a misunderstanding on my end. So I don't.
Okay, well, it's possible that if you entered anything related to papers for the test, so it was question 9 was the one that is different. It looks like that they're not getting the right answer because I did it in REML, so it's a different result.
Yeah, no, I just meant this entire section. Like
Oh, okay.
ICC.
Yes, okay, yes.
It's a misunderstanding issue.
So the binary variables of employment and quantitative training, you use 3.29 for the residual variance in computing the interclass correlation. And for papers, since it's just like what we've been doing, there's an estimated residual variance that you can use in the denominator, just like normal. Mm-hmm.
Yeah, because I know how to calculate them, but the output just looks different than what I'm used to. So finding the value I'm supposed to use is my.
Okay. Okay. Yeah, we can look at that if you'd like. Okay. So, all right. So other questions while we're here on homework? No?
Just finish section 1.
That's okay. It's not due till Friday. I'm just asking. My objective, by the way, was for you guys to be able to leave on Thanksgiving break and not think about this class for a week. Wouldn't that be nice? Honestly, like finish your work and then you're done, right? So this is the time of year where there's a lot of conferences and there's a lot of illness, and it's just, we all need a break, right? We all need a break. Okay, so I'll ask again on Thursday if you have other questions. And yes, you can always email me and say, this is what I think the answer is, this is how I got it, and it's not working, and I can check to see that I haven't screwed something up or help point you in the right direction. So, but this week is a special week, I would say, because we're deviating from the official topic of clustered data to show sort of how these models are related to other things that you know. So there's an expression that if you have a hammer, everything is a nail. Do you know that expression? What it means is that you try to solve problems with the tools that you have available. So like literally, if the only tool you have is a hammer, then you try to hammer everything with it. And so it's a phrase like everything is a nail. So as an example, I once tried to put up a towel rack in my apartment. And I realized that it came with screws and it said to drill a hole. Did I have a drill? No, I was in college. So do you know what I did? I hammered the screws into the wall. And, it was a little wobbly, but it got the job done. I'm sure the people who came after me were horrified, but I had a towel rack. So yeah, that phrase is often used sort of because I'm always fond of saying everything is a multi-level model, and it is. If you have a hammer, everything is a nail. Everything is a nail. I'm here to tell you that. So multi-level models, because random effects and latent variables are the same thing, you're learning a lot more than just how to analyze clustered data. You're learning techniques that translates to other things. And so that's what today is. It's about the intersection between what are so-called measurement models and multi-level models. And this is where the idea that we have, people who specialize in measurement or statistics breaks down, because this is measurement and statistics at the same time. There really is no distinction between the two. Measurement models are used for different purposes, but they are statistical models and they're multi-level models. So this is what I wanted to talk about. And on Thursday, we're going to have a crash course in longitudinal. And then after you come back from break, we'll be doing 3-level models in which one of the levels is time, so that you do get some practice with longitudinal and clustered at the same time. How about that? Yay, yes. Because I don't know when longitudinal's coming back. I only had 4 people in it last semester, so they probably won't let me do it again for a long time. But everything's online. I have a YouTube channel. I also have given a gazillion longitudinal workshops, and so those are on my website too. So if you want the crash course that isn't a whole semester, you can do those. But all right, so away we go. So some of this is taken from a talk that I gave elsewhere. It was actually embedded in my job talk at KU, and some of this was embedded in my job talk here. So if you went to that, you may recognize a few things, but it has some story in it, and hopefully you will enjoy it. So the Hofflin Lego-based view of quantitative methods. This is, so Hofflin is my son's last name. It's Hoffman and Templin put together. His name is Hugh Hofflin. Yeah, we did that. You can do that. Yeah, so we sort of refer to our household as the Hofflin household, And we came up with this a long time ago, as the idea of if you were to drill down quantitative methods into certain key elements, what would they be? And we liken it to the idea of Legos, right? You all know what Legos are. Little toys, you put them together and you make all sorts of amazing things if you want to. But the blocks themselves are pretty simplistic. It's how you put them together that gives you things that are far from simplistic. So these are the 4 building blocks that we think of in terms of what you need to know to be able to do quantitative methods, either to use it to do research or to study quantitative methods. Linear models is the first thing. So that was where we started off this semester, with reviewing linear models, interaction terms, nested effects, all that kind of stuff. You have to know a little bit about estimation, because the days of calculating sums of squares and whatnot end with very, very simple models. We don't calculate things, we estimate them. Link functions is what we've been talking about lately, right? What's a link function again? Like logit? They're things that transform the predicted outcome into a more continuous version that your linear model can predict. I have a whole class about them next semester. We're going to do link functions of all different kinds, as well as univariate and multivariate data and path models. But then the last one. And I lump these together because these are all the same thing that go under different terms. Random effects, latent variables, latent traits, latent factors. The idea that you have this common variability. And it is, in our context, we've been talking about modeling multivariate data. So if you have, say, a school that has multiple students sampled, one way of looking at it is that it's a multivariate set of observations for the school. There's also truly multivariate. Longitudinal data fall into that category as well as for modeling relations of unobserved constructs. So we have the linear models part, we have estimation, we've talked about that, and what other blocks you need is dictated by how your outcome is measured and your dimensions of sampling. So if you think about the idea of collecting multiple sources of data on any unit, it could be students in a school, it could be occasions for a person, it could be items to measure a trait. One way of thinking about it is that you have random effects. So for instance, in longitudinal data, if I have 4 occasions at level 1 nested in persons at level 2, the very first thing you'd want to figure out is how much of your variation is between persons or within persons. This semester, we have people nested in groups. And the very first thing you want to figure out, such as section 1 of your homework, how much of your outcome variation is between groups or within groups. And so you have these variance components that are estimated by the model to try and partition that variance. Well, you do the exact same thing in the context of measurement models. So a measurement model is a way to link an item response to an unobserved trait that the item is supposed to be measuring. So in the same way that we have time nested in person, we might have items nested in people. And the items, you're trying to distinguish how much of their variability is because of the trait you're measuring, the latent variable, latent factor, latent trait, those are all synonyms, and how much of it is unique to the item that doesn't have to do with the latent trait. So this is quite literally the same thing done for different reasons. So the models that you have been learning this semester, and lately switching over to logits, are measurement models. That's another way that these models get used. So we tend to refer to these unobserved quantities that are estimated by the model as random effects when they're used for handling dependency. So the idea that people from the same class are more related than people from different classes, outcomes from the same person are more related than outcomes from different people. And so this introduction of random effects is what triggers the name mixed model, because you have fixed and random effects, or what I call multi-level, or what also may be known as a hierarchical linear model. Those are all synonyms. Instead of thinking about dependency, we would use the term latent trait or factor or variable if we're talking about measuring something that is unobserved, but it's still the same idea. The trait that is being measured by the items is supposed to be the reason the items are correlated, right? Like the items should have nothing to do with each other if they're not measuring something in common. If they are measuring something in common, then we try to estimate how much of their variability is in common, and we give that a name. We call it the trait, right? And we try and estimate how much of the variance in the item is because of that trait. So it's the same type of approach. It's just we don't use the word dependency in that context. And so random effects and latent variables are really, really powerful techniques because they allow us to make sense out of multivariate data. They allow us to be able to quantify different sources of variation for different reasons and predict them. And we can also avoid getting rid of data by summarizing things unnecessarily. So I want to tell you a story. So this is a real story. This is going back to my graduate school. By the way, when I left graduate school, I could just barely run proc mixed. Like I knew enough to make it go and not enough to make it like go the right way for sure. Okay, so that's where I was. I was just learning about multi-level models when I was out with some colleagues. These are some people that I went to graduate school with and where they are now. And this is Larry. And Larry was, we were shooting pool, and he was bummed because he had just had a paper rejected. And so we were trying to ask him, like, well, what happened with it? And he's like, oh, my F2 wasn't significant. I'm like, what the hell's an F2? Well, he told us a story. So Larry does psycholinguistic types of research where he asks people, for instance, to quickly as possible decide if a set of letters is a word or a not word. And then he manipulates things about the letters to like learn about language and whatnot. And in Larry's field, there were rules about how you had to analyze the data from these experiments. And you were supposed to do 2 different kinds of ANOVAs, what was known as an F1 or an F2. And I had never heard of F2, so he explained it to me. And this is how it works. So let's say that you have 2 different manipulations for your stimuli, and each has like a low level and a high level. And so you create stimuli, items, that follow these manipulations, and let's say that you have 100 items of each type, so each cell, so to speak. So each person has 100 response times of each kind, 400 total. Well, what they do is first aggregate the items that are supposed to be the same kind and compute a mean for that person for each cell. So they assume, without testing, that all of these 100 items that they made to be in the same kind are exactly the same, so much so that you can just take the mean over them. And that's also necessary because, as you might imagine, not everybody will have a response time for every item. In this field, it is traditional for any items that were answered incorrectly to have their response times deleted because they don't know what the mechanism is that generated the incorrect response. So they take this multivariate data, summarize it, and do a repeated measures ANOVA, so within persons is what I would call it, where we have a random intercept for persons. So this is the univariate approach to repeated measures. That's your F1. And because this is a person level analysis, the more people you have, the more power you have. The other way that they want you to analyze your data is what's known as an F2. And it's the opposite way of aggregating the data. You aggregate over the people, and you end up with the mean response time for every possible item. And then you analyze the differences between items, which are independent, with a between groups type of ANOVA. And in this approach, the more items you have, the more power you have. And there's no random effects needed. And so in his field, in order for the effect of whatever you've manipulated here that distinguishes your items to be believable, both of these ANOVAs have to be significant. And Larry's F2 was not significant, and that's why he was bummed. And I thought, well, this is sort of crazy. Like, each of these is wrong, right? You're aggregating over information, assuming that it doesn't matter. And at the time, I was thinking, well, I'm learning this multi-level modeling stuff, and maybe it can fix it, and we can save Larry's paper. So I was like, oh my God, this is brilliant. So I'm gonna have items nested in people, and so then we can have our level 1 model for what distinguishes the items, factor A and factor B and their interaction, and here's my random intercepted person, and I can do it on all the data. I don't have to aggregate, and it can be missing at random for the incomplete responses. And I was like, cool, this is great. The only problem is that this is still wrong. I didn't realize this at first. It was actually someone else who figured this out, and I went to a talk at a conference, and they were talking about this problem, and I was like, holy shit, they're right. Multi-level modeling isn't going to save the world because this is still wrong. This is functionally the same F1 ANOVA, where we're paying attention to differences between persons, but we're assuming that differences between items are perfectly explained by these A and B factors. There's nothing in the model that accounts for the differences among items of the same kind. There's nothing in there. So I had to fix it. So what I had done is think about it this way, where we have items at level 1 and persons at level 2. But in the same way that some people are faster than others as a trait, some items are responded to more quickly than others as a characteristic of the item. So what I was thinking of as sort of within person variation across items, I actually needed to separate out as between item variation and trial-specific variation. So when you put it all together, a given item is predicted by which item it is, because some items are systematically different than others, and which person gave me the answer, and that combination creates a unique trial. So trial is level 1. Persons and items are both level 2, and they're crossed. So we wrote a paper. It was published in 2007 using Larry's data as an example for a different data set. And this is what the model then would look like. So rather than writing it in 2-level notation, I just wrote it as combined. So this is the same logic by which we did crossed primary schools and secondary schools a couple weeks ago. Remember that? It's a cross model. So the response time for any trial for a person for an item is a function of these item characteristics plus a random effect of person plus a random effect of item. So this explicitly accounts for the fact that the responses to the same item are going to be related. Just like U in red here accounts for the fact that responses from the same person are going to be related. And so then you have the potential to examine what proportion of this item variance was explained by A, B, and their interaction. And this variance here for persons is unconditional because there's no people predictors. So I posted a bonus example that I did at a workshop in Illinois on Halloween is where it's posted if you're more interested in this, but here's the summary. He had a data set for something else that he allowed to lend us, so it is real data. It had roughly the same amount of people and words, and so we had about equal power. And so we had 2 different types of predictors. And the empty model before adding in the predictors, the decomposition of variance looked like this. So of all the variability in response time, 24% of it had to do with some people are faster than others. 11% of it had to do with some words were responded to more quickly than others. And 65% was residual. So let me stop before I show you the results. These 2 predictors that he's interested in, and this is very common in their sorts of designs, are item things. What is the maximum total variation that his model can capture? 11%, right? So he's not even targeting the other 89% because he doesn't have any predictors that have to do with why some people are faster than others or why some trials have different response times than expected based on who it was and which item. So there's something tricky about that combination. We don't know any of that. So it worked out that of the variability across items, his A and B factors and their interaction accounted for 30% of that. So this model can be used to explicitly test whether or not his items were exchangeable, whether or not there's significant variance across items that remains after putting all the reasons in why the items were supposed to differ. And it looks like 70% of that wasn't in the model. So they really weren't exchangeable. We did a little simulation study in it was in chapter 12 actually of my book, so that was me doing it, basically showing that type 1 error rates are going to be wrong if you test item effects using a person ANOVA model, and if you test person effects using a item level model. So the same thing that we've been talking about, the predictors that go with that pile of variance need that pile of variance to be represented in the model. So this is all for response time. That brought up the question as to when items need to be random. When is it the case that you need this crossed model? So one is if the fixed effects already explain all of the item variation. So going back to Larry's data, if he only had 4 items, right? And then these 4 fixed effects would explain all the reasons why those items differ from each other, and there's no item variance left to worry about. So if you have saturated the model, you put in a fixed effect for every different item, then you don't have to worry about this. In other sorts of studies from my former life and as a cognitive person, things are nested in persons like memories, eye movements. In that case, it's pretty clear that that's a straight nesting and not a crossing. But in other situations, you do have to worry about this. And so this is the tie between measurement models and multi-level models. So I want to introduce you to a world known as explanatory IRT models, because you actually already know what that means. So how many of you have had a class on factor analysis or item response theory? A couple people? Yeah, most people. Okay, well here's your class. I get to do it next fall, by the way. I'm going to be doing my version of SEM, which is, it ties together CFA, IRT, and SEM. But there is a model for the probability of a correct response that looks like this. So for Y for a person and an item, the probability that it's 1 is a function of two things in this model. This is what's known as a one-parameter logistic model. It is also known as a Roche model. And theta, this red thing, that is a person's ability. It's the latent trait that the item is supposedly measuring. B is an item parameter. In this case, it is difficulty. The definition of difficulty is that it is the trait level. I get my other hat on. It is the location on the latent trait at which the item has a 50-50 probability of being correct. Did I get that right? Okay, good. Oh, by the way, I fixed one of the slides in the last lecture where we did the quadrature, because that had an IRT example built in and I didn't catch it because I knew this was coming. So I did fix that, by the way. So this, do you see the different forms? This is the logit, right? So if we write the model as predicting the logit, it simplifies greatly. The only thing that makes this weird is the minus sign. So rarely in linear models do you see something subtracted. It's usually added, but that's different. So this model says that items differ from each other in their difficulty. Each item gets its own difficulty estimate. So items are treated as fixed effects. Persons are treated as random, because we don't estimate a theta for each person. What we do is estimate its variance instead. That model is a multi-level model also. Here's the correspondence. If I put in item as a categorical predictor, meaning I put in dummy codes for all the different items, each item would have its own fixed effect. Because if they're added together, it would be easiness rather than difficulty. So the direction is backwards, but it's the same idea. And what we know this semester as a random intercept is theta. It's the same. So in this case, items are treated as fixed. So we are removing differences between items. Level 1 is still the crossing of item and person, and level 2 is person. Now, identification. When you are estimating this model, you have to decide how to identify it, because theta is an imaginary thing. It doesn't exist. So you have to give it a scale. So the way that theta is identified, meaning it has a mean and variance, you fix something to 0 and something to 1. So you can fix one item difficulty to 0. You can fix the sum of the item difficulties to 0. That's another approach that some programs take, or just the theta mean. Say that theta has a mean of 0. On the variance side, you either have to fix the item discrimination, so that is an imaginary slope that's out here that's not written, or the theta variance to 1. As a generalized multi-level model, this same model is identified by having theta have a mean of 0 the random intercept, and have its variance be estimated. So there's no different slopes relating the item. They have different difficulties, but not different slopes. So any difference across programs can be characterized as a difference in identification. You can either say that there is a slope of 1 and estimate theta's variance, or you can estimate the common slope and fix theta's variance to 1. So IRT programs often fix theta's mean to 0 and its variance to 1, whereas when it's written as a multi-level model, the variance is estimated instead. But it is literally the same thing. So one of the things that I did in my dissertation was develop a new measure, and I manipulated item difficulty in the measure. And what I had learned at the time from Susan Embridson was something called the linear logit test model, LLTM. Does that ring a bell, IRT people? It's the idea that you can put predictors as to why some items are more difficult than others. So if I do that written as a multi-level model, I am making a very strong assumption now, because I am not controlling for the differences in difficulty across items by letting them each have their own difficulty. I'm saying that difficulty can be predicted by a linear combination of item predictors. So it's actually making the same mistake that I did for Larry's data by not thinking about the fact that items have to have a variance left over. And so, for instance, this is what I did for my dissertation was measure visual search ability in the context of driving. And what it is a experimental paradigm called the flicker paradigm, where you show a picture, and in between that and the next picture, there is a blank gray screen that goes up for 80 milliseconds, and then the picture comes back, blank screen, slightly different picture, and then it comes back. So it looks like it's flashing at you. And what happens is that the flash interrupts your process of looking through the picture so that it's not immediately obvious how they're different from each other. So if you were to just stare at them side by side, how are these pictures different from each other? Yeah, the exit. So it's real easy to stare at them side by side, but it's surprisingly difficult to find this. And so search through the picture is an effortful process that we can measure the efficiency of which with this task. So anyway, there were 4 features of these things that I manipulated to make the pictures more or less difficult. And relative to what I reported in my dissertation, I will show you this analysis. The model that doesn't have a random item effect, I had all kinds of significance. It's published. It's in Educational and Psychological Measurement, 2009, I think, maybe. It's wrong. It's so wrong. But you know what? They can't take my PhD back. They can't take it back. But I now know that only one of my effects was significant and tested in the right model. So this idea that you can have differences in item difficulty or easiness be predicted by features of the items in the same way that you can predict why some people have more ability than others, this is a field called explanatory item response modeling. It is a crossed random effects model with a logit link. So I have a random intercept for people. That would be predicted by person things. I have another random intercept for items, all the reasons why some items are more difficult than others that you can predict with item characteristics. And then you have an unestimated level 1 variance because it's a logit. So let me show you how you can do IRT models using proc glymics and stata. How cool is that?
Super cool.
I know, right? And so the next time someone says, are you measurement or statistics? You can roll your eyes like I do and be like, both? Because they go together. So here's example 6. This is real data collected from my dissertation. We are predicting the accuracy of finding the change to those signs within a 45-second period. And so I have item predictors. as to how cluttered the picture was, whether the change made was relevant to driving, the physical salience of the change measured in the size of the pixels changed, and whether or not the change was made to a legible sign, which is a factor I discovered post hoc mattered. So the data structure to do this analysis is stacked. It's just like it would be in any other multi-level model, where level 1 is a row. So each row is a single item response for a single person. So here is a model treating items as fixed in the sense that there's nothing in the model for them, and persons is random. So I have theta in here as my, actually no, this is single level model, excuse me, that's the next one. So this is no random effects whatsoever as a benchmark. So I have a logit for percent correct of 1.2. That translates into a probability of 0.78. So that's my average rate of correctness before I factor in any random effects. If I add in a random intercept, still an empty model. So this model is assuming that all items are equally difficult, but that some people are better at this task than others. They're more prone to have correct responses. So here is my random intercept variance / theta variance. That's what it means. Do I need that theta variance? Likelihood ratio test relative to the previous model says yes I do, and I verified that this result is actually correct. You'll see what happens later on when it actually doesn't work. So this is the model that I ran in my dissertation. That's wrong. It is the linear logistic test model. I think that's what LLT stands for. It's a model developed in the 70s. So it's pretty old in that sense, back when people didn't know any better. So I am putting in my 4 predictors as to why I think some of these pictures are going to have higher rates of accuracy than others, what makes some of the pictures more difficult. And lo and behold, I get lovely significant results. Everything is significant. So at the reference point for all of these things, I have a logit intercept of 0.86. The log odds, the logit of accuracy, goes down if it's a more cluttered picture. It goes up if the picture is more relevant to driving. It goes up if the change is more visually salient, and it goes up if I have a legible sign. Next model, Roche model with random subjects and saturated fixed items. So I'm using Glimmix to estimate a 1-parameter logistic model, or what's known as the Roche model. So this is treating items as a fixed effect in that each item gets its own easiness because it's additive and not subtracting. So picture is going in on the model, and it's also on class. The analog to that in Stata is I.dot. So what am I doing there? What does it mean if I have picture on the class statement or I put an I.dot in front of it in Stata? It's categorical, meaning it's going to make dummy codes for me. So this version of the model, I left in the general intercept. So each of these dummy codes is going to give me the difference between one picture, that's the reference, which is the last one, and each of the others. I have a multivariate wald test for the differences across items and their logits, which is significant, meaning they do vary from each other in how difficult or how easy they are. I have theta variance that's even bigger, because part of the reason why I had level 1 variance is now being explained by which picture it is. So whenever you explain level 1 variance, level 2 variance goes up in these models. And I asked for the least squares means. These are the easinesses in logits for all my different pictures. Now what if I wanted to properly account for these differences between items and their easiness and test my hypotheses about why they are there. Can I use this model? Can I use a model where each item gets its own separately estimated easiness and then predict why some items are more easy than others? Can I do that? Can I do both at the same time? So this model right here has fixed effects for every possible item. There's 36 items, so I have 35 fixed effects. That generates a predicted mean for each item in terms of how easy it is on the Logit scale. Can I have a separate mean for each item and predict why some items are more difficult than others? Nope, it's redundant. But I don't want to do the wrong model, where I don't have any differences between items except for the ones that I've predicted. So I need to add items as a random effect. So this is an empty crossed model. This is the beginning of what would be called an explanatory item response model, where I have two different random intercepts. One that would be for subjects, which is my theta, and one that is for items. So why some items are more difficult than others is now a variability source to be predicted. Now I have two Cove tests here trying to ask whether each of those sources of variability, differences between persons and ability, and differences between pictures and easiness are necessary. And watch what happens. It's like, no, you don't get to know that, sorry. No idea. Sometimes it does this. So I had to get Excel out and look at the differences in -2 log likelihoods myself. So it did get this one, it crapped out on this one. But what I'm asking for here is something new, the word solution. You're used to seeing it on the model line because that gives me the solution for fixed effects. When you put it on the random line, it gives me the solution for random effects. Those are my thetas. So I'm using Laplace estimation in this example because that's required when you have crossed random effects in a logit link. It's also the default in Stata. But now I have two variance components. So the first one for part ID, that's all the reasons why some people are more likely to be correct on this task than others, ability. And this one is all the reasons why some pictures were more likely to be answered correctly than others. So there's a lot more variability between pictures than persons. Each of these estimates is from the solution for random effects. So they have a mean of 0 for the random effect because the mean is given right here. So that number right there is the mean easiness in logits. And then each of these values in the table is how far off from the mean that particular item is in its easiness. So if you want to put their offness together with their mean, then you get the easiness per item. And that's what I had done up here, is create a new column that has that.
Why is there is no covariance between picture and person?
Because they're crossed. You can't have a covariance between them in this case, because they're two different dimensions of sampling. And the reason why there's no covariance is because they're on two separate random lines. If I had somehow wanted them to have a covariance, I'd have to put them on the same line. And actually, that's possible to do in SAS, but it's hella tricky. The only situation in which I've seen crossed models where you would have different covariances across the dimensions is in like those sorts of studies where everybody rates each other, like round robin sorts of designs, like social networky kinds of things, because then it's like your theta as a rater needs to be correlated with your theta as a ratee, because it's the same person, and that's tricky to set up, but possible if you're willing to do some extra coding. But in this situation, differences between pictures are separate from differences between people. So here, the reason this is cool, I still have a way of trying to estimate how difficult a given item is. It's phrased in easiness, but it's the same concept. But now this model, by estimating a variability across them directly, allows me to see how much of the differences between items are due to my manipulations. So the last model then puts it all together. We have clutter, relevance, brightness, legible sign, and a random effect of items. So this model explicitly allows me to test how much of the variability across items were due to the things that I have listed here. Whether or not items are exchangeable beyond that. So this is what's known as an explanatory item response model. So of the variability across items relative to the empty model, it's down about 25%. So 25% of all the reasons why some items are more difficult than others is because of the four things that I measured or manipulated here. And that means there's a whole lot of item variance up for grabs that I don't know why it's there. The differences in the results, though, are pretty severe. The only thing that matters now significantly is whether or not the change was made to a legible sign. So I'll put the slide back up that compared these things. Here it is. So the difference in these sets of results. On the left is a model that says the only reason for differences between items are these four things. It allows no extra relationship from the responses from the same item. After you factor this in, that's supposed to be it. And so these standard errors are based on level 1 variability. Over there, on the other side, it has an extra random intercept for items that allows for remaining differences across the items for unknown reasons. And so the relevant source of variability is then the basis of the standard error. And so these are much higher. So this is the correct model. The wrong one, unfortunately, is in print. Sorry about that, world. But the beauty of these is that you can do all of this at the same time in terms of looking at predictors. So you can put subject variables in the model to explain theta variance. You can put item predictors in the model to explain item variance. And the results, I wanted to compare what the item parameters look like across these different methods. So there are 4 different models. So there was the fixed B, meaning each item got its own easiness as a categorical predictor. That's the distribution of that variable. There is this one, where items were treated as random, and it was an empty model with no predictors. And these things are pretty darn close. It looks like the fixed model has a lower bound, so there's a little bit of shrinkage here from the random effects, but they're almost perfectly correlated. So there is the correlation between the fixed effects Roche model and the random intercepts for the items. It's the same. I also computed what the predicted difficulty would be from the LLTM that doesn't have the corresponding error term for the differences between items, and this one as well. And you can see that these ended up being fairly similar. So it's not the estimates that were the problem from the model, it was the standard errors. And they are very highly correlated as well. So this is IRT. Everything is a nail. But one thing that isn't talked about in IRT that we can examine here is more than one reason for differences between people. Theta is a random intercept. This framework also allows us to examine random slopes. So it is possible that some of these manipulations affected some people more than others. So I can have an item predictor have random slope variance over people. The effect of the item could be more salient for some people than others. And so in the example that goes with this, I tried each of these in turn, and none of them happened to be significant, but that's an addition that this modeling framework allows you to do. So that's pretty cool. So what do you think? Mind blown? This is all the same stuff. It's just interesting how it gets talked about differently in different contexts.
I'm thinking that how to link multidimensional IRT into this generalized multilevel framework. So there will be several person variants because there are several dimensions.
Mm-hmm.
Okay.
It would, so are you thinking of multidimensional IRT in the sense of every item loads on every theta, or just like there's more than one theta?
There is no cross-loading. Just
No cross-loadings.
Yeah.
Yeah, so what you would have to do is rather than having intercept here, you would have to put in custom intercepts that would distinguish which items go with which theta. So basically you would create dummy variables that link that theta to that item and put those in instead of intercept. And so they would be off for the items that don't measure it and on for the items that do. Because this would be constant across.
And each dimension at least have 4 items be loaded on that dimension. You said saturated.
3 to be identified and 4 to be
3.
testable, I guess, yeah. Most of the time in this framework, it's a unidimensional model, but there's no reason it has to be.
Okay.
Yeah. Yeah. So what about studies in which we have students taking tests in schools? What could we do there? 3-level? So that's a multi-level IRT putting it together. You could end up with level 1 being differences between items, so long as you have saturated the model, meaning that each item gets its own easiness, it doesn't have to be an extra random effect. And then you would have thetas at level 2 and thetas at level 3 for schools. And so variability in ability would be partially due to between school differences and partially due to within school differences. So yeah, that's where the world goes, higher and higher. So, questions, thoughts?
So can I link the Roche model to, if I put the context into G theory, like calculate the B equal?
This is G theory.
What?
This is G theory. Yeah.
Okay, so can I use the variance like components to calculate the B coefficients?
So yep, if you, I am not a G theory scholar, but what I know is that if you have multiple sampling dimensions, right? Like give me a G theory example, somebody.
measure, say, 200 people over 2 different occasions.
Mm-hmm. So in that case, you have variance due to people, variance due to time, people by time. You have, I guess, the 5 scales could be multidimensional, or it could be like you think of that. But yeah, you can put in random effects for all of those sources of variance. That's G theory. And different statistics that you can calculate are proportions of variance, right? So if I had raters and subjects and items, like to do reliability, right? So if you wanted to have a reliability check, you have more than one coder go through the same procedure for the same targets, right? And you want to know how reliable your coding is, it would be that the only reason for the variability in the data is differences between the targets, not the raters. So yeah, these models are G theory also. So everything is a multi-level model, people. That's what I've been telling you. The difference is the link. By the way, did you know that you can do factor analysis with proc mixed? Uh-huh. You don't believe me? Let me get you latent trait, bonus example time. Let me find it. 4. Okay, so this is from my version of SEM. So we go through this whole rigmarole in M+ to do single factor models, identification, blah, 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 model fit, blah, blah, stuff, more stuff, words, and proc mixed. So in SEM context, in the world of CFA for continuous outcomes, you have a null model in SEM, right? That model has different means across items and different variances but no covariances. So that would look like this, where you put item in as a categorical predictor. You allow different variance across the item but no covariance whatsoever. So this is a heterogeneous Toeplitz matrix with only one diagonal being estimated. So that's my null model. The other baseline in SEM is a saturated model, right? That's the best model. That means you have saturated means, so each item gets its own mean, same here, and each item gets its own variance, and all possible covariances, right? We call that unstructured. So that's your other baseline. If you wanted to do a single factor model, that is type equals FA with one factor, factor analytic. And the solution gives you the residual variance of each of your items as well as the loadings. Everything is a multi-level model, even confirmatory factor models. So if you wanted to do confirmatory factor analysis, and you could do it in proc mixed, however, to do it for more than one factor is tricky, but you can do it in that. So, and do it with REML too, by the way, because that's the other thing, is that structural equation modeling is all about ML. So, see, do you believe me now? Cool, huh? All the stuff is the same under the hood. It's all the same. All right, you're not nearly as excited as I am. But I felt really cool when I figured this out, though. It was one of my favorite comps questions to ask people. Explain how item response theory is a multi-level model. She's like, really? But the comps that I'm thinking of are like the take-home kind, like you write a paper kind, not like you dump your head in a room kind, because homie don't play that. So anyway, there. Thoughts, questions? Anything else you want to know about this while I'm on a roll?
What for the GPL model?
Knew someone was going to ask that. That one is tricky. That one amounts to a heterogeneous variance model. So, with respect to theta, you cannot do it in Glimmix. We have tried, so it's not possible.
So it's still like a two-level modeling.
Mm-hmm. It's the way that you can pull this off is because the method of identification is such that you're estimating the theta variance, which means that discrimination is 1, so it doesn't have to be estimated. If you have to estimate discrimination, you can't do it in this way. So it's a software limitation, not a modeling limitation. It's just not designed for that. But back before there was proc IRT, I used proc NL mixed to do IRT models. I have examples using that. If you are interested, I can show you that. But you can write out any model you want in the world with NL mixed. 1PL, 2PL, 3PL, 4PL. I don't know if there's any more than that. Have they come up with 5 and 6 yet? No? Okay. Yeah, IRT is like the most boring set of names, right? Like, what comes after 1? I don't know, 2? Let's call it that. Anyway. Others? Questions, thoughts?
For the homework, I still come back to number 9, and I try to change the method to the remote. I think I also have to change the method from the Gmax to the mixed, right? Because that is why, but it's contradictory. That is why now I understand, because if you want to use the link, you have to do Gmax, and then that's why.
Yeah, you can use just regular mixed for anything that's normal with identity.
Fix to use the Gmax for that particular one, or you want us to use, because you use the identity, and then you have to use the Gmax, right?
Glimmix, yes.
Right? So you are going to change it, we don't have to do it.
Proc mixed uses a normal distribution and an identity link. Like, that is what it uses. You just have to be explicit about it if you're using Glimmix, but I believe that is the default.
Can you say that again?
When you run mixed in Stata or SAS, that is an identity link and a normal conditional distribution.
Okay, so I can't, okay, so I have to change it because when I use the clean mix, and then I don't have such a method at all.
So I'm going to fix it so that it is consistent with the instructions. I'm going to fix it. Okay. Other thoughts, questions? All right, let's call it a day, folks. How about that? Like 5 whole minutes early. Woo! I'm going crazy. So office hours start now. I will see you on Thursday for the crash course in longitudinal.